This video is going to illustrate obtaining some of the solutions for exercise set number 4 using the internet searches and online tools. So exercise set 1, we're supposed to read a document that is provided in the lesson, and it's the one Robertson, closed conduit flow. And if we read that, the relevant answers are in the first few pages. There's the energy equation. So Z1 must correspond to elevation at point 1. HP is the head supplied by a pump. P2 over gamma is the pressure head at location 2 in the system. Alpha 2 V2 squared over 2G is the velocity head at position 2. Z2 is the elevation at position 2. H sub T is the head supplied to a turbine, and H sub L is the head loss between sections 1 and 2 from pipeline friction, fitting losses, and similar loss terms. Moving down, it says the value alpha in alpha V squared over 2G is called the kinetic energy correction factor. And the closest here is kinetic energy correction factor, so the answer would be B. If there's laminar flow in the pipe, the velocity distribution will be parabolic, and hence alpha will have a value of 2. The answer is D. If the flow regime is turbulent, alpha falls in the range 1.04 to 1.06, which would be the answer B. And 1.04 to 1.06 is close enough to unity to be adequate. Number 5, actually none of the correct answers are there, and we'll determine that in a second. It says, what's the power required to pump 1 cubic feet per second into 100 feet ahead? We're simply going to use the power equation here, and the values we have are, I think I want to use comment. Hopefully it'll let me do some typing. There we go. So we have P equals Q gamma H, which in our case is equal to 1 cubic feet per second. Gamma is 62.4 pounds per cubic foot of water, and the added head is 100 feet, and so that equals 624 6240, and this is going to be in pound feet per second. So we're going to need to turn 6240 pound-feet per second into cubic feet per second. So let's get ourselves a new tab. CONVERT pound feet per second into horsepower. There's a converter here, and so we want to convert 6240. When we tell it to convert, it's 11.3, and so this particular problem has none of the answers are correct. However, if the problem is stated in as 10, which was the intent, 62,400, in that case, 62400, we calculate and we get 113, which would have been the intent. So the correct answer for this problem is there is no correct answer. So we'll go ahead and include that, which I guess I can do is, so this is equal to 62400 times 0.0018. I shall cheat. WSD-06-0018. All right, next one, relative roughness, K sub S for a 5-foot diameter rivet steel pipe. So we want roughness, height, riveted steel pipe. And we have some choices. I think I chose this one. Does not have riveted steel as an option, so we'll go back. We'll try that one. Clearly has the word riveted steel. It says riveted steel is 3,000 to 30,000. Let's use the higher one, 30,000. So we now need to convert that. So it's 30,000 times 10 to the minus 6 feet. 30,123 times 1e minus 6 equals 0.03 is the roughness height, and relative roughness is that value divided by the diameter. So we divide that by 5, press the equal sign, 0.006, so the correct answer is C. Okay, 7, 8, and 9, that was really what I made the video for, was to show how to do these. So for number 7, we're going to have a 6-foot diameter rivet steel, so we know that the roughness height is 0.03, and we can use the online tool iteratively to find the approximate head loss. So we go to our online tool, discharge given head loss, and we're going to supply it with the pipe diameter, which is 6 feet, gravitational acceleration 32.2 for its customaries. Now the head loss is the unknown value. Let's just pick one for now. Do 10 feet of head loss. Pipe length is 10,000 feet. Roughness height 0.03, and we need a value for kinematic viscosity 1e minus 5. Let's be 1.22 minus 5. That should get us at about 50 degrees Celsius. Hit the submit, and it says under those conditions we get a discharge of 100. So we need to increase our estimated head loss value. So we'll double it. Let's go to 20. Hit submit. We're at 140. So we need to increase it again. Let's go up to 30. Hit submit. We're at 174. We'll go up to 33. Hit submit. We're at 183. Go to 36. Hit submit. We're at 191. We're pretty close. And I'm guessing 39 will get real close. 39 is 199. So the head loss for this one is roughly 39 feet of head. And that was simply using Darcy-Weisbach model. About 39 feet. Okay, we play the same game with Hazen-Williams. We go to our pipeline calculator, we choose head loss in Hazen-Williams as customary. We need to look up the riveted C. Projecting growth in horizontal rivets, a value of 100 is suggested. So we use our loss coefficient of 100. Diameter is 6 feet. Length is 10,000 feet. And the value of discharge in this problem is 200. Let it solve for the head loss, 27.49 feet. So that completes the first 8. And we'll pick up the next 8 in another video.